The Pacific Ocean does not warn you. It doesn't send a memo. It doesn't give a press conference. It simply begins, somewhere between the tropics, as a cluster of thunderstorms rotating over water so warm it might as well be a furnace. And then it grows, hour by hour, feeding on heat energy that has been accumulating in the upper ocean layer for months, energy ultimately delivered 93 million miles away by a star 864,000 miles wide that has been burning for 4.5 billion years. The Typhoon does not belong only to Earth, not really. When meteorologists at the Joint Typhoon Warning Center in Pearl Harbor, Hawaii, classified Typhoon Mawar as a Category 4 storm in the spring of 2023, the sustained winds had already reached 150 miles per hour. The central pressure had collapsed to 920 millibars, lower than the weight of the atmosphere that humans evolved to breathe. At that pressure, the air itself becomes something alien. The eye wall, a vertical cylinder of convective fury climbing nearly 11 miles into the sky, was releasing energy equivalent to 10,000 nuclear warheads every single day. Not over its entire lifespan. Every single day. That number deserves a moment of stillness. The bomb dropped on Hiroshima in 1945, released approximately 15 kilotons of energy in a single world-altering instant. A mature Category 4 typhoon, at peak intensity, dissipates the thermal energy equivalent of 10,000 of those events, not in one explosion, but in the relentless, churning, continuous work of organized atmospheric convection. A hurricane or typhoon is not a disaster. It is a heat engine, one of the most efficient thermodynamic machines the planet has ever produced. And it is heading toward United States soil. Guam, a United States territory in the Western Pacific, home to 163,000 people and critical American military infrastructure, sat directly in the path of Mawar as the storm peaked in late May of 2023. The island, 30 miles long and 4 miles wide at its narrowest point, had nowhere to go. The storm, with a diameter of over 300 miles, was larger than the island by a factor of 10. When two systems are that asymmetric in scale, the physics becomes unambiguous. Guam would receive the storm, not deflect it. What does it mean for a small island to receive a Category 4 typhoon? The answer is not simply a lot of wind. Wind is one variable in a system so interconnected that pulling on any single thread unravels the whole fabric. Storm surge, the dome of ocean water physically lifted and pushed ashore by wind and low pressure, is the deadliest component of any major tropical cyclone. During Typhoon Haiyan in 2013, the most intense tropical cyclone ever recorded at landfall, storm surges of up to 21 feet obliterated entire coastal communities in the Philippines. Water weighs 62.5 pounds per cubic foot. A wave containing millions of cubic feet of seawater moving at speed does not merely flood a structure. It removes it from existence. Mawar, while not reaching the catastrophic intensity of Haiyan, still generated storm surges observed between 5 and 8 feet across Guam's vulnerable coastlines. For communities built at sea level, which on a small Pacific island is most communities, the distinction between a 5-foot surge and an 8-foot surge is the distinction between damaged and destroyed. The meteorological mechanics of how a tropical disturbance becomes a Category 4 typhoon are not mysterious. They are, in fact, one of the most well-understood processes in atmospheric science. That understanding does not make the outcome any less violent. It makes it more profound. Tropical cyclones, called hurricanes in the Atlantic and Eastern Pacific, typhoons in the Western Pacific, and cyclones in the Indian Ocean and South Pacific, are the same phenomenon wearing different regional names. They require 3 fundamental ingredients: warm ocean water of at least 79 degrees Fahrenheit, extending to a depth of at least 160 feet, an atmosphere that cools rapidly with altitude, and low vertical wind shear, meaning winds at different altitudes must be traveling at roughly similar speeds and directions, so they do not tear the developing storm apart. The Western Pacific is the most active tropical cyclone basin on Earth. It generates more storms, more frequently, and at higher intensities than any other ocean on the planet. The reasons are structural. The Western Pacific is warmer, wider, and less disrupted by the land masses that constrain Atlantic hurricanes. A storm forming east of the Philippines has an enormous fetch of open water over which to travel and intensify. It has time, and in atmospheric thermodynamics, time is everything. Sea surface temperatures in the western Pacific have been rising measurably for decades, driven by the absorption of excess thermal energy from a planet whose radiative balance has been altered by increasing concentrations of greenhouse gases in the atmosphere. The connection is not theoretical. The ocean has absorbed approximately 90% of the excess heat trapped by the enhanced greenhouse effect since the pre-industrial era. That heat does not disappear. It is stored. And tropical cyclones are the mechanism by which the ocean releases stored thermal energy back into the atmosphere. What scientists have documented, through satellite observations, aircraft reconnaissance data, and ocean buoy networks spanning millions of square miles, is a measurable trend toward rapid intensification events. Rapid intensification is defined as an increase in maximum sustained winds of at least 35 miles per hour within 24 hours. These events were already considered rare. They are becoming less rare. Typhoon Mawar intensified by 50 miles per hour in a single 24-hour period. The ocean beneath it was not merely warm. It was anomalously warm, with heat content extending far deeper than historical averages, deep enough that the churning of the storm could not upwell cooler water quickly enough to cut off the energy supply. When a storm cannot cool the water beneath it fast enough, the thermodynamic feedback loop remains unbroken. Heat evaporates into moisture. Moisture rises. Rising air releases latent heat. Latent heat warms the column further. The warm column rises faster. Pressure at the surface drops. Pressure drops accelerate surface wind inflow. Wind inflow supplies more moisture. More moisture means more latent heat release. The storm breathes itself into existence. There is a common misconception that typhoons and hurricanes are chaotic, random, unpredictable events, acts of nature that defy scientific understanding, remnants of the era when storms were seen as expressions of divine wrath. This is simply incorrect. The physics governing tropical cyclone formation, intensification, and movement have been rigorously documented since the middle of the 20th century. The first successful aircraft reconnaissance flight into a hurricane eye was conducted in 1943, when two Army Air Forces pilots flew a single-engine trainer into a Texas hurricane on a bet. What they observed inside, the eerie calm, the cloud walls rising impossibly high, the thermodynamic structure, began a tradition of manned hurricane reconnaissance that continues to this day, operated by the National Oceanic and Atmospheric Administration's Hurricane Hunter Fleet. Every major tropical cyclone that threatens populated land today is tracked continuously by reconnaissance aircraft, polar orbiting satellites, geostationary satellites, ocean buoys, and numerical weather prediction models running on some of the most powerful supercomputers ever built. The National Weather Service's global forecast system ingests millions of observational data points every 6 hours and produces track and intensity forecasts extending to 16 days. The European Center for Medium-Range Weather Forecasts, considered the gold standard of global numerical prediction, operates a model so computationally expensive that a single forecast run would take years on a conventional laptop. And yet, with all of this infrastructure, with all of this data, with all of this computational power, the rapid intensification of tropical cyclones remains one of the most difficult forecast problems in operational meteorology. The processes governing whether a storm jumps from Category 2 to Category 4 in 18 hours are partially driven by small-scale convective dynamics inside the eye wall that no current observation network can fully resolve. The ocean heat content beneath the storm, at depths of 300 feet, is sampled by a sparse array of Argo floats that drift passively through the ocean, providing data at intervals of days, not hours. The forecasters who tracked Mawar toward Guam knew the storm was dangerous. What they could not know with certainty until the reconnaissance data came back was precisely how dangerous. That uncertainty, bounded, quantified, scientifically honest uncertainty, is not a failure of science. It is science working exactly as it should. The acknowledgement of what is not yet known is what separates a scientific forecast from a guess. And when the data finally resolved, When the Doppler radar aboard NOAA's WP-3D Orion aircraft painted the interior of Mawar's eye wall in vivid detail, the numbers confirmed what the warm Pacific had been silently promising for weeks. This was not a borderline storm. This was a machine. And machines this efficient do not stop until they run out of fuel. The question that kept the forecasters at the Joint Typhoon Warning Center awake at their terminals was not whether Guam would be struck. The track models had converged on that answer days earlier with unusual agreement. The question was what this machine would do next, because Guam was not the only landmass in Typhoon Mawar's path, and the fuel supply in the Western Pacific in the late spring of 2023 was nowhere near exhausted. The Western Pacific has a memory. It stores heat, the way thick stone walls store the warmth of a fire long after the flames go out. The upper 200 feet of the ocean in the Philippine Sea and the waters east of the Mariana Islands function as a thermal reservoir of staggering capacity, one that has been accumulating excess energy for decades, responding to an altered planetary energy balance that has been shifting measurably since the mid-20th century. When Typhoon Mawar crossed over this reservoir in late May of 2023, it was not drawing on a normal ocean. It was drawing on an ocean that had been quietly charged, degree by fraction of a degree, year after year, until the fuel available at the surface and at depth exceeded anything the storm's internal thermodynamics could fully exhaust in a single pass. The critical variable was not just surface temperature. That is the number most often cited in news coverage, and it matters, but it tells only part of the story. What the reconnaissance data and the Argo Float network revealed beneath Mawar was an ocean heat content anomaly extending to depths that fundamentally changed the storm's intensification ceiling. Under normal conditions, a powerful typhoon churning through the ocean acts as its own brake. The winds drive surface currents that push warm water aside and drag colder water up from depth, a process called upwelling. As cooler water reaches the surface, the sea surface temperature drops. The temperature differential between the ocean and the atmosphere decreases, the engine loses fuel pressure, and the rate of intensification slows. This is one of the ocean's natural regulatory mechanisms. It is elegant, automatic, and well documented across decades of cyclone research. But it requires a cold reservoir at depth close enough to the surface to be reached by wind-driven mixing. In regions where anomalously warm water extends deep enough, the upwelling mechanism is compromised. The storm churns, mixes, and lifts, and finds warm water all the way down. The brake fails to engage. In 2023, the Western Pacific was in the grip of a developing El Niño pattern. El Niño, formerly the El Niño Southern Oscillation warm phase, is a periodic redistribution of heat across the tropical Pacific, driven by the weakening of the trade winds that normally push warm surface water westward. When those winds relax, the warm water they have been piling up against Asia and Australia sloshes back eastward in a slow, massive thermal wave. The Pacific reorganizes itself. Sea surface temperatures rise across the central and eastern Pacific. Atmospheric circulation patterns shift across the entire hemisphere. Rainfall that normally falls over Indonesia falls instead over Peru. Drought replaces monsoon in parts of Australia. The jet stream over North America migrates. And in the Western Pacific, the already warm surface waters receive an additional thermal charge that pushes ocean heat content anomalies to levels not seen in the instrumental record. The instrumental record of ocean temperature is not long by geological standards. Systematic measurements using standardized methods began in earnest only in the mid-20th century. The Argo program, a global array of nearly 4,000 autonomous profiling floats that drift with ocean currents, periodically diving to depths of 6,000 feet and measuring temperature and salinity on their way back to the surface, was only fully deployed by the mid-2000s. Before Argo, deep ocean heat content data was sparse, uneven, and dependent on ship-based measurements that sampled only a thin fraction of the world's oceans. What Argo revealed, once it reached full deployment, was sobering. The ocean was warming not just at the surface but at depth, and faster than climate models had predicted even a decade earlier. The rate of heat uptake in the upper 2,000 meters of the global ocean has roughly doubled since the 1990s compared to the preceding 4 decades. That energy does not vanish. It circulates. It redistributes. And in the Western Pacific, it accumulates in a basin already predisposed by geography and ocean circulation to be the warmest stretch of open water on the planet. Consider the scale of what this means in physical terms. Water has a specific heat capacity of approximately 4,182 joules per kilogram per degree Celsius, meaning it requires that much energy to raise 1 kilogram of seawater by a single degree. The Western Pacific Typhoon Basin covers roughly 15 million square kilometers. The upper 100 meters alone of that basin contains a volume of approximately 1.5 quadrillion cubic meters of water. Warming that volume by even a fraction of a degree Celsius represents an energy input measured in exajoules, units so large that the entire global annual electricity consumption of humanity amounts to only about 80 exajoules per year. The ocean is not just warm. It is an energy storage system operating at a scale that dwarfs every power plant, every fuel reserve, every human energy infrastructure combined. Mawar was tapping into that system. The storm's central pressure at peak intensity dropped to 920 millibars. To understand what that number represents physically, consider that standard sea-level atmospheric pressure, the pressure humans experience on a calm day at the beach, is 1,013 millibars. The difference between a calm atmosphere and the core of a peak-intensity Category 4 typhoon is less than 100 millibars. That sounds modest. It is not. Pressure is force per unit area. A column of air over every square meter of ocean surface inside Mawar's eye was exerting nearly 9.5% less force on the water below than the surrounding atmosphere. The ocean surface responded the way any fluid responds to reduced pressure above it. It rose. The low pressure at the center of Mawar physically lifted the sea surface by approximately 3 feet in the eye before the storm even made landfall. That dome of elevated water, pushed by winds and driven ashore, was the storm surge. The relationship between central pressure and storm surge is one of the most well-established empirical relationships in tropical meteorology, refined over decades of post-storm surveys and tide gauge data. Every millibar of pressure drop below ambient conditions contributes approximately 1 centimeter of hydrostatic surge. But the wind-driven component amplifies this base level dramatically, depending on the coastal geometry, the shape of the seafloor approaching shore, the angle of the coastline relative to the storm track, the width of the continental shelf. Guam's steep volcanic underwater topography provides less of the gentle sloping shelf that amplifies surge catastrophically in places like the Gulf of Mexico coastline. This geological accident, the fact that Guam rises steeply from deep ocean floor rather than from a gradually shallowing shelf, was the primary reason the storm surge at Mawar's landfall, while destructive, did not reach the catastrophic levels seen during Gulf Coast hurricanes of comparable intensity. The wind field was another matter. Typhoon Mawar's tropical storm force winds, sustained speeds above 39 miles per hour, extended outward approximately 315 miles from the center in some quadrants. For context, the entire island of Guam is approximately 30 miles long. A person standing at Guam's northernmost point and a person standing at the southernmost tip were both experiencing tropical storm force winds simultaneously, while the eye wall, the zone of maximum winds, was located somewhere in between. The asymmetry of the wind field meant that the northern half of Guam, which experienced the stronger right front quadrant of the storm's circulation relative to its direction of motion, received sustained Category 4 winds for several hours. The right front quadrant of a moving tropical cyclone consistently produces the most extreme conditions because the storm's own translational speed adds directly to the rotational wind speed in that sector. A storm moving westward at 15 miles per hour generates maximum winds on its northern flank that are 15 miles per hour, stronger than identical storms would produce if they were stationary. This asymmetry has been understood theoretically since the early work on tropical cyclone dynamics in the 1950s and 60s, pioneered by researchers including Herbert Real at the University of Chicago, and later refined by Carey Emanuel at MIT, whose work on the thermodynamic limits of hurricane intensity in the 1980s produced the concept of potential intensity, a calculated upper bound on how strong a tropical cyclone can become given a specific sea surface temperature and atmospheric profile. Immanuel's potential intensity framework, grounded in Carnot cycle thermodynamics, the same physics that governs the maximum efficiency of any heat engine, demonstrated mathematically that tropical cyclones are not arbitrary or chaotic. They are operating within precise thermodynamic boundaries set by ocean temperature above and the cold tropopause aloft. Raise the ocean temperature, and the theoretical ceiling rises. The storm has permission to become stronger. What Immanuel and subsequent researchers could not fully specify in the 1980s was the rate at which storms would approach that ceiling, whether warmer oceans would produce storms that intensified faster, reached their potential intensity more reliably, or maintained peak intensity for longer durations. These questions required decades of additional observational data, the development of coupled ocean atmosphere models capable of simulating the interaction between storm-driven mixing and the thermal structure of the ocean, and the global coverage provided by the modern satellite era. The answers, assembled piece by piece through hurricane reconnaissance data, satellite microwave imagery capable of seeing through clouds into the storm's warm core, and ocean profile data from Argo and deployed dropsondes, have been converging toward a consistent conclusion. The proportion of storms that reach major hurricane or typhoon intensity, Category 3 or above on the Saffir-Simpson scale, has increased. The rate of rapid intensification events in the Atlantic and Western Pacific has increased. The latitude at which storms reach peak intensity has been shifting poleward, exposing coastlines that historically experienced weaker decaying systems to storms at or near peak strength. These are not projections. These are measurements. When Mawar reached Category 4 status and aimed itself at Guam, every one of those measured trends was visible in a single storm, a rapidly intensifying system, a deep warm ocean that refused to allow upwelling cooling, a peak intensity reached over water that, historically, storms in that region reached only closer to the Philippines after additional time over the open ocean. The storm was, in a precise scientific sense, ahead of schedule. The question the atmospheric scientists and oceanographers were quietly asking each other in the days before landfall was not only about Guam. Guam, as catastrophic as the impact would be, was a 30-mile island. The storm's forward motion would carry it across the island in hours. What concerned the longer-range forecasters was the water ahead, the South China Sea and the waters between the Philippines and Taiwan, still warm, still laden with the heat content of an El Niño-charged Pacific, waiting like an open furnace for a storm that had already demonstrated it knew how to feed. Friction is the reason you are alive, not metaphorically, literally. The surface of the Earth, its mountains, forests, coastlines, and plains, exerts frictional drag on moving air that dissipates kinetic energy, slows wind, and disrupts the organized circulation of atmospheric vortices. Over land, this drag is substantial. A tropical cyclone crossing a coastline immediately begins losing its primary energy source, warm ocean water, while simultaneously encountering increased surface roughness that tears at its wind field from the bottom up. The lowest few thousand feet of the storm's circulation, the boundary layer where the atmosphere interacts directly with the surface, begins to decouple from the organized convection above. The eye wall weakens, the pressure gradient relaxes, the machine runs out of road. Over open ocean, none of this applies. Between Guam and the Philippine archipelago lies approximately 1,500 miles of open western Pacific water. After Mawar crossed Guam on May 25th of 2023, it emerged on the western side of the island, still carrying Category 1 sustained winds, weakened, disorganized, but structurally intact. The eye wall had partially collapsed during the land interaction, a common and well-understood response to the disruption of the inflow layer by terrain. But the ocean ahead was waiting with the same thermal reservoir that had built the storm in the first place. The question atmospheric scientists were running model ensembles to answer was precise. Would the storm's remnant circulation, its vorticity and residual warm core, survive long enough over open water to allow re-intensification before reaching the Philippines? Vorticity, the measure of rotation in a fluid, is one of the most conserved quantities in atmospheric dynamics. A spinning column of air resists losing its spin the way a gyroscope resists changing its orientation. This property, rooted in the conservation of angular momentum, means that even a weakened tropical cyclone retains the organized rotation that makes re-intensification possible as long as the environmental conditions support it. The storm does not need to rebuild its structure from scratch. It needs only to reconnect its existing rotation with the thermodynamic fuel of a warm ocean surface and a favorable upper-level atmospheric environment. Angular momentum itself is a concept worth pausing on. It is the product of a rotating mass, its velocity, and its distance from the axis of rotation. In a tropical cyclone, as air spirals inward toward the low-pressure center, the radius of rotation decreases. To conserve angular momentum, because no external torque is acting on the air parcel in the free atmosphere, the velocity must increase as the radius shrinks. This is precisely the same physics operating when a figure skater pulls their arms inward during a spin and accelerates dramatically without any additional muscular effort. The skater does not add energy. They redistribute existing angular momentum into a smaller radius. A tropical cyclone is executing this same physical operation continuously across millions of tons of air sustained over days. The specific geometry of Mawar's re-intensification track placed it over sea surface temperatures that ranged between 84 and 86 degrees Fahrenheit, 5 to 7 degrees above the minimum threshold required for tropical cyclone maintenance. At those temperatures, the evaporative flux from the ocean surface into the atmospheric boundary layer is intense. Water molecules at the surface absorb solar radiation, gain enough kinetic energy to escape the liquid phase, and enter the atmosphere as water vapor, carrying with them the latent heat of vaporization, approximately 2,500,000 joules per kilogram. That energy is invisible while the water exists as vapor. It is released explosively when the vapor condenses back into liquid droplets inside the towering convective cells of the eye wall. 2,500,000 joules per kilogram. To contextualize that figure, a kilogram of TNT releases approximately 4,600,000 joules upon detonation. The latent heat released by condensing a single kilogram of water vapor inside a typhoon's convective column is equivalent to slightly more than half a kilogram of high explosive, released not in a single violent instant, but continuously, across millions of kilograms of condensing water vapor cycling through the eye wall every second. The total latent heat release inside a mature typhoon's convective system per second has been estimated at quantities exceeding the combined output of every electrical power plant currently operating on Earth. This is not an exaggeration for effect. It is a dimensional analysis result derived from measured precipitation rates, storm geometry, and the thermodynamic properties of water. The eye wall itself, the annular ring of convective towers surrounding the calm eye, is one of the most physically extreme environments that exists in the natural atmosphere of this planet. The updrafts inside a mature tropical cyclone eye wall have been measured by reconnaissance drops on instruments at vertical velocities exceeding 40 miles per hour. Air entering the boundary layer near the ocean surface, loaded with moisture and heat, is accelerated upward through the eye wall at speeds that carry it from sea level to the upper troposphere, altitudes exceeding 50,000 feet, in under 30 minutes. As it rises, it cools adiabatically, releasing its latent heat, warming the surrounding column, and driving the pressure drop at the surface that sustains the entire system. At the top of the eye wall, this air spreads outward in the upper troposphere as the storm's outflow layer, a vast canopy of cirrus cloud that can extend hundreds of miles from the center and is clearly visible in satellite imagery as the diffuse white shield surrounding the tight spiral bands below. The efficiency of this outflow, how cleanly the spent air can escape the storm's circulation aloft, is one of the key determinants of how intensely the storm can develop. When upper-level winds are strong and directional, high vertical wind shear, this outflow layer is disrupted. The warm core is ventilated with cooler environmental air, and intensification is suppressed. When upper-level winds are weak, and the outflow can radiate symmetrically in all directions, the thermodynamic cycle runs at maximum efficiency. During Mawar's re-intensification phase west of Guam, vertical wind shear across the storm's track remained below 15 knots, well within the range that operational forecasters classify as conducive to intensification. The upper-level anticyclone, the high-pressure circulation aloft that acts as the exhaust valve for the storm's outflow, was positioned favorably to the northeast, pumping spent air away from the storm's core efficiently. Every component of the atmospheric environment was permissive. The storm had survived land interaction. It had a warm ocean beneath it. It had a clear atmospheric pathway above it. Re-intensification was not a possibility. It was an inevitability. The physics of tropical cyclone re-intensification after land interaction had been studied extensively in the context of Western Pacific typhoons, precisely because the regional geography, chains of relatively small islands separated by large expanses of warm open water, creates repeated natural experiments. Typhoon Megi in 2010 crossed Luzon in the Philippines and re-intensified over the South China Sea to reach Category 5 intensity. Typhoon Haiyan in 2013 passed over several Philippine islands before its catastrophic Leyte landfall, weakening and then rapidly re-intensifying over the warm waters between island groups. The pattern is not coincidental. It is a predictable consequence of the ocean's thermal structure and the typhoon's inherent thermodynamic resilience. What makes the Western Pacific uniquely dangerous, more so than any other tropical cyclone basin, is precisely this combination of factors. The density of populated island chains, the expanse of warm water between them, and the frequency with which major typhoons can execute multiple intensification cycles across a single track. A storm that strikes one island at Category 2 intensity, weakens to tropical storm force over the terrain, and then re-intensifies to Category 4 or 5 over open water before reaching a second landfall is not a theoretical scenario. It is a documented, recurring event in the historical typhoon record. The atmospheric scientists tracking Mawar west of Guam were watching the model ensembles with the particular attention that comes from knowing the stakes of the forecast. The Philippines, an archipelago of over 7,000 islands with a population of approximately 115 million people and a coastline stretching over 22,000 miles, was the next major land barrier in the storm's path. Unlike Guam, the Philippines presented not 30 miles of terrain but hundreds of miles across multiple major islands, with Luzon, the largest, most populous island, home to Metro Manila and its 13 million residents, sitting squarely within the range of projected tracks. The forecast models were not converging with the same agreement they had shown before the Guam landfall. The post-land interaction track of a weakened but re-intensifying typhoon over the South China Sea involves interactions between the storm's circulation and the complex terrain of the Philippine archipelago, the position of the subtropical ridge steering the storm, and the evolving upper-level pattern across East Asia. Small differences in the initial conditions, the precise intensity and structure of the storm's remnant circulation over the Philippine Sea, propagated into large differences in track and intensity forecasts at 5 and 7 days. The ensemble spread, the range of possible outcomes across dozens of model runs initialized with slightly different starting states, was wide. Wide ensemble spread is the forecaster's honest acknowledgement that the atmosphere at that moment is in a state where small perturbations matter enormously. It is not a failure of the models. It is the models accurately representing the sensitivity of the system. Edward Lorenz, the MIT meteorologist, whose work in the early 1960s laid the mathematical foundation for chaos theory, demonstrated that certain states of the atmosphere are inherently unpredictable beyond a finite time horizon. Not because the physics are unknown, but because the atmosphere is a non-linear dynamical system in which arbitrarily small differences in initial conditions grow exponentially with time. The famous butterfly effect is not a poetic metaphor. It is a mathematical property of nonlinear systems, proven rigorously and observed repeatedly in operational forecast verification data. Mawar, west of Guam, churning over 85-degree water under favorable shear, was sitting at precisely the kind of sensitive decision point Lorenz's mathematics described. The storm could track north of Luzon and avoid the main island mass. It could recurve early into the East China Sea. It could thread through the Philippine island chain and emerge into the South China Sea for a final intensification run before a Vietnam or southern China landfall. Each scenario carried its own casualty potential, its own storm surge geography, its own population exposure. The ocean did not care about any of these scenarios. It simply continued to offer heat. The forecast models were wrong. Not catastrophically, not in the way that produces post-event investigations and congressional testimony, but wrong in the specific, operationally consequential way that matters most when a major typhoon is bearing down on a populated coastline. The ensemble guidance that had been tracking Mawar toward a Philippines landfall scenario shifted. The steering flow, the broad-scale atmospheric current that carries tropical cyclones the way a river carries a boat, reorganized. A ridge of high pressure that had been anchoring itself across the northwestern Pacific strengthened and expanded westward, effectively building a wall of sinking air that deflected Mawar's track northward. The storm that meteorologists had been watching with one eye on Luzon turned instead toward Taiwan and the waters south of Japan. This was not a random event. It was a predictable consequence of the same large-scale atmospheric dynamics that govern every tropical cyclone track, but predicted with certainty only in retrospect after the atmosphere had already made its choice. The steering of tropical cyclones by the large-scale pressure field is one of the oldest and most studied problems in tropical meteorology. A tropical cyclone has no preferred direction of motion on its own. It is carried almost passively by the mean flow of the atmosphere through a layer extending from roughly 5,000 to 40,000 feet, a depth-averaged wind that meteorologists call the steering current. The subtropical ridge, the belt of high pressure that girdles the planet between approximately 20 and 35 degrees of latitude, is the dominant steering mechanism for most of the lifetime of Western Pacific typhoons. Storms embedded on the southern and western flank of the ridge track westward. Storms that reach the ridge's northern edge begin to recurve, turning first northward, then northeastward, as they encounter the westerly winds that dominate the mid-latitudes. Recurvature is one of the most difficult forecast problems in operational typhoon prediction, precisely because the timing is so sensitive to the exact position and intensity of the ridge. A ridge that is 2 degrees of latitude farther north than forecast produces a recurvature track that misses the Philippines entirely and threatens Japan instead. A ridge that holds its position 2 days longer than forecast means a direct Luzon landfall. The atmosphere does not negotiate these differences on human timescales. It resolves them on its own schedule, and the consequences, in terms of which populated coastlines bear the impact, are enormous. What the operational forecasters at the Joint Typhoon Warning Center documented in real time during Mawar's post-Guam track was a classic recurvature event driven by a strengthening mid-latitude trough over the central Pacific. A trough, a region of lower pressure and cyclonic curvature in the upper-level wind field, acts as an atmospheric vacuum that draws tropical cyclones poleward and then eastward as they approach. The trough that reorganized Mawar's track was not unpredicted. It was in the model guidance. But its precise timing and amplitude, the factors that determined whether Mawar would recurve before or after reaching the Philippines, were at the edge of predictability at the forecast lead times, when protective actions would have needed to be initiated in Manila. This is the fundamental tension at the heart of operational tropical meteorology. The social need for certainty collides with the physical reality of atmospheric chaos. Evacuation orders, prepositioning of emergency supplies, mobilization of military assets, all of these actions have lead time requirements measured in days. The atmosphere's predictability horizon for typhoon track, in sensitive cases involving recurvature near a steering ridge boundary, can be shorter than those lead times. Forecasters are therefore required to communicate probability, cone of uncertainty graphics, ensemble spaghetti plots, exceedance probabilities for wind and surge, to populations and decision-makers who frequently interpret probabilistic guidance as deterministic prediction. The consequences of this communication gap are not abstract. After Typhoon Haiyan devastated the Philippines in 2013, post-event analyses revealed that despite accurate track and intensity forecasts, the storm surge warning, which ultimately accounted for the majority of the more than 6,000 confirmed deaths, was not effectively communicated or understood by coastal populations who had no prior experiential frame of reference for a surge of up to 21 feet. Warnings were issued. The warnings were not translated into protective action at the scale required. The gap was not scientific. It was cognitive, institutional, and infrastructural. The World Meteorological Organization's post-Haiyan review produced a set of recommendations that fundamentally changed how tropical cyclone hazard communication is conducted across the Western Pacific. The shift from wind speed-based categorization as the primary public communication tool toward impact-based forecasting, describing not the storm's meteorological parameters, but the specific, localized consequences for life and infrastructure, represented a philosophical reorientation of an entire forecasting culture that had operated on the Saffir-Simpson wind scale framework since its introduction in 1971. Herbert Saffir, a structural engineer, and Robert Simpson, then director of the National Hurricane Center, developed the scale originally as an engineering tool, a way to communicate expected structural damage to buildings and infrastructure at different wind speed thresholds. It was never designed as a comprehensive hazard communication instrument. Its adoption as the primary public-facing descriptor of tropical cyclone danger produced a generation of coastal residents who understood Category 5 as maximally dangerous and Category 1 as relatively benign, a framing that systematically underweighted storm surge, rainfall flooding, and the compounding effects of multiple hazards that often cause more casualties than wind alone. Mawar, at Category 1 intensity during its post-Guam phase over the Philippine Sea, was still generating seas of 20 to 25 feet in its immediate vicinity. A Category 1 designation on public broadcasts carried an implicit message of reduced threat. The seas 25 feet high surrounding the storm's center did not receive that message. The recurvature that redirected Mawar northward spared Luzon from a direct strike. The storm passed to the north of Luzon, with its outer rain bands delivering significant rainfall to northern portions of the island, triggering landslides and flooding across mountainous terrain that recorded over 10 inches of rain in 24 hours in some locations. The distinction between a direct Category 3 or 4 landfall on Metro Manila and the glancing blow delivered by Mawar's outer circulation is a distinction measured in thousands of lives and hundreds of billions of dollars in infrastructure. It is a distinction that was determined, ultimately, by the position of a high-pressure ridge over the northwestern Pacific, a feature measured in thousands of miles and governed by the same planetary-scale atmospheric dynamics that have been operating since long before the first human civilization built a structure close enough to a coastline to be threatened by storm surge. The scientific community's understanding of how climate change is altering the behavior of the subtropical ridge, and therefore the preferred tracks and recurvature climatology of Western Pacific typhoons, is one of the most active and consequential research areas in current atmospheric science. Observational studies published in journals including Nature Climate Change and the Journal of Climate have documented a poleward expansion of the subtropical dry zones, a widening of the Hadley circulation, and a corresponding shift in the average latitude at which typhoons reach peak intensity. These shifts have measurable implications for which coastlines bear the greatest future risk from major tropical cyclones, implications that extend far beyond the Western Pacific to include coastlines in the subtropics and mid-latitudes that have historically experienced only weakening systems. Japan, a nation with sophisticated typhoon preparedness infrastructure built over a century of experience with major landfalling systems, has documented an increase in the frequency of typhoons reaching the Japanese main islands at near-peak intensity, with less time for weakening over cooler waters than historical climatology suggested. South Korea has seen analogous trends. The poleward migration of peak intensity latitude is not a future projection contingent on emission scenarios. It is a trend already present in the observational record, detectable in satellite-era data extending back to the 1980s. Mawar's recurvature toward Japan placed it on precisely this emerging risk track. As the storm turned northward and then northeastward, accelerating in forward speed as it became embedded in the mid-latitude westerly flow, it encountered cooler sea surface temperatures that began to suppress convection and erode the warm core. The transition from a tropical cyclone, a warm core system deriving energy from ocean evaporation, to an extratropical cyclone, a cold core system deriving energy from temperature contrasts between air masses, is called extratropical transition, and it is itself a phenomenon that the meteorological community has spent decades trying to forecast accurately. Extratropical transition does not simply mean a storm weakens and disappears. It means the storm's energy source and structure change fundamentally. An extratropical transitioning typhoon can actually expand its wind field dramatically even as its maximum sustained winds decrease, producing gale and storm force winds over an area far larger than the original tropical cyclone covered. It can also interact with the mid-latitude jet stream in ways that amplify downstream weather patterns, accelerating the formation of new storm systems thousands of miles away. The transition of a major western Pacific typhoon into the extratropical zone is not a local event. It is a perturbation to the hemispheric circulation that propagates downstream across the Pacific and can influence weather patterns over North America 5 to 7 days later. The storm that began as a cluster of convection east of the Philippines that built itself into a Category 4 typhoon over anomalously warm Pacific water that struck Guam, threatened Luzon, recurved toward Japan, and finally transitioned into an extratropical system in the northwestern Pacific, left a signature in the global atmospheric circulation that extended far beyond the path of destruction visible in satellite imagery. Every typhoon does. The atmosphere is not a collection of isolated events. It is a single, continuous fluid, and every perturbation propagates. What Mawar demonstrated, with a precision that made it nearly a controlled experiment in tropical cyclone behavior, was the full life cycle of a major Western Pacific typhoon operating in an ocean that is measurably warmer, deeper, and more energetically charged than the ocean that shaped the typhoon climatology of the 20th century. The rapid intensification. The deep warm water that frustrated upwelling cooling, the anomalous heat content extending to depth, the recurvature sensitivity, the extratropical transition. Every phase of the storm's existence bore the fingerprint of an altered ocean. The fingerprint is not a metaphor. It is a measurable, quantifiable signal extracted from decades of ocean heat content observations, sea surface temperature records, and tropical cyclone intensity data. A signal that climate attribution scientists can now isolate and quantify using the same statistical methods applied to any other geophysical dataset. The signal says the same thing in every dataset, in every ocean basin, in every decade of the satellite record. The ocean is warmer. The storms know it. At peak intensity, a tropical cyclone is the closest thing the atmosphere of Earth produces to a perfect thermodynamic machine. Not metaphorically, not approximately, precisely. In the technical sense that atmospheric physicists use when they apply the Carnot cycle to a rotating fluid heated at the base and cooled at the top. Carey Emanuel's foundational work demonstrated that the maximum wind speed achievable by a tropical cyclone is governed by the same mathematical relationship that determines the maximum efficiency of any heat engine operating between two thermal reservoirs. The warm reservoir is the ocean surface. The cold reservoir is the upper troposphere near the tropopause, where temperatures plunge to negative 112 degrees Fahrenheit at altitudes approaching 60,000 feet. The greater the temperature difference between these two reservoirs, the higher the theoretical ceiling on storm intensity. It is thermodynamics operating at planetary scale, indifferent to anything beneath it. When Mawar reached its peak intensity on May 24th of 2023, the central pressure had dropped to 920 millibars, and maximum sustained winds had reached 165 miles per hour, placing it at the high end of Category 4 on the Saffir-Simpson scale, within measurable distance of Category 5 threshold. The reconnaissance aircraft threading through the storm at that moment were not flying into a weather event. They were flying into a fully realized atmospheric heat engine operating near the upper bound of what the current thermodynamic state of the Western Pacific could theoretically support. The reconnaissance data from those flights represent some of the most detailed in-situ measurements ever taken inside a peak-intensity Western Pacific typhoon. The NOAA WP-3D Orion aircraft that penetrated Mawar's eye wall recorded boundary layer winds, temperature profiles, moisture content, and pressure at altitudes from sea surface to 40,000 feet using GPS drop-ons, small instrument packages deployed from the aircraft that fall through the storm on parachutes, transmitting data at 1-second intervals until they hit the ocean's surface. Each drop-on descent through the eye wall of a peak-intensity typhoon produces a vertical profile of atmospheric conditions through one of the most extreme environments on Earth, resolved at vertical intervals of approximately 30 feet. What those profiles reveal inside a peak-intensity eye wall is a world governed by physics operating at its limits. The pressure gradient, the rate at which pressure changes with horizontal distance, inside the eye wall of a major tropical cyclone is steeper than in any other naturally occurring atmospheric phenomenon on Earth, except a tornado. In Mawar's case, pressure was dropping at a rate that, extrapolated linearly, would represent a change of over 80 millibars across a horizontal distance of roughly 15 miles between the outer eye wall and the calm eye center. No other feature of Earth's weather system concentrates a pressure gradient of that magnitude across that spatial scale in sustained, organized fashion. The gradient wind balance, the three-way equilibrium between the inward pressure gradient force, the outward centrifugal force, and the Coriolis force acting on rotating air, is what keeps the eye wall in its annular structure rather than collapsing inward or expanding outward. This balance is not static. It is continuously maintained by the storm circulation against the perpetual tendency of any pressure gradient to flatten itself through the movement of air from high to low pressure. The eye wall sustains itself only because the inflow of warm, moist air at the surface continuously replenishes the energy lost to friction, precipitation, and outward radiation. Remove the ocean heat source and the balance collapses within hours. The storm decays from the inside out. The calm eye at the center of this system, the region of light winds, clearing skies, and anomalously warm temperatures that reconnaissance pilots have been documenting since 1943, is itself a consequence of the dynamics of the surrounding eye wall, not a separate phenomenon. The intense convection in the eye wall drives subsidence, slowly descending air, in the eye region. Descending air warms adiabatically at a rate of approximately 5.5 degrees Fahrenheit per 1,000 feet of descent. Air subsiding from upper tropospheric levels through the full depth of the troposphere warms by dozens of degrees, creating the anomalously high temperatures in the eye column that constitute the tropical cyclone's warm core and drive the low surface pressure below. The warmest temperatures in the storm are not at the ocean surface. They are aloft, in the upper levels of the eye, where the air has descended from the coldest part of the troposphere and been compressed and warmed to temperatures that can exceed the surrounding environment by 15 to 20 degrees Celsius at altitudes of 40,000 feet. This upper-level warm anomaly is the thermodynamic engine's exhaust, the signature of the Carnot cycle operating in a rotating fluid. Satellite-based microwave sounders can measure this warm core from orbit, providing a remote sensing pathway to tropical cyclone intensity estimation that does not require aircraft penetration. The intensity of the warm core signal correlates directly with the maximum sustained wind speed at the surface. At Mawar's peak, the warm core anomaly measured by the AMSUA microwave sounder aboard the NOAA-18 satellite was among the most intense recorded in the Western Pacific Basin in the 23-year AMSU observational record at that time. The instrument, operating at 57 gigahertz, a frequency at which oxygen in the atmosphere absorbs microwave radiation in proportion to temperature, was effectively taking a temperature reading of the air column through the entire depth of the atmosphere, resolving the storm's thermal structure in 3 dimensions from an altitude of 540 miles. The same satellite that measured Mawar's warm core also tracked the sea surface temperature cooling wake left behind as the storm passed. Typhoons and hurricanes leave a cold track on the ocean surface. A trail of cooler water stretching hundreds of miles along the storm's path, persisting for days to weeks after passage, created by the vertical mixing and upwelling driven by the storm's wind stress on the ocean surface. Mawar's cold wake, measured by the MODIS instrument aboard the Aqua satellite, showed sea surface temperature depressions of 2 to 4 degrees Celsius, extending along the storm's track east and north of Guam. That cold trail is the ocean's receipt, the thermal record of the energy extracted by the storm during its passage. 2 to 4 degrees Celsius of cooling across a surface area of hundreds of thousands of square kilometers represents an enormous transfer of heat from ocean to atmosphere. The energy has not been destroyed. It has been converted, partly into the kinetic energy of the storm's wind field, partly into the gravitational potential energy of lifted water, partly into the latent heat released by precipitation, and partly radiated outward to space through the storm's high cloud tops. The accounting of this energy budget across a major tropical cyclone's lifetime is one of the more complex exercises in observational atmospheric thermodynamics, requiring integration of satellite data, reconnaissance observations, ocean measurements, and numerical model output across the full spatial and temporal extent of the storm system. The precipitation alone from a major typhoon represents a staggering hydrological event. Typhoon Mawar produced rainfall accumulations exceeding 20 inches in some areas of Guam during its passage, in a storm that crossed the 30-mile island in a matter of hours. Rain gauge measurements from the Andersen Air Force Base weather station recorded over 15 inches in less than 12 hours. The physical mechanism driving this precipitation intensity is the same one driving the storm's winds. The convergence of moisture-laden boundary layer air into the eye wall updrafts, which carry water vapor from sea level to the upper troposphere in the time it takes to drive across a small city. The total water vapor transport through a major tropical cyclone's circulation in 24 hours has been estimated at quantities exceeding the total annual discharge of the Amazon River, the largest river system on Earth, which pours approximately 6.6 million cubic feet of fresh water into the Atlantic Ocean every second. A peak-intensity typhoon moves more water vertically through the atmosphere in a single day than the Amazon delivers horizontally to the ocean in a year. This is not a peripheral fact about extreme weather. It is a fundamental statement about the role of tropical cyclones in the global hydrological cycle. Their function as the primary mechanism by which the tropical ocean sheds its accumulated heat and moisture to the atmosphere, redistributing energy and fresh water across hemispheric scales. Without tropical cyclones, the heat accumulated in the tropical ocean over summer months would have no efficient release mechanism. The thermodynamic imbalance between the tropics and the poles, the fundamental driver of all atmospheric circulation, would be larger, and the compensating poleward heat transport by other atmospheric systems would need to increase accordingly. Tropical cyclones are not aberrations in the climate system. They are components of it. They are doing a job. The devastation they leave behind on human timescales, the flattened structures, the inundated coastlines, the disrupted ecosystems, is the consequence of that job intersecting with the geographical accident of populated coastlines. The storm does not target coastlines. It does not distinguish between a reef and a city. It moves where the steering flow carries it, intensifies where the ocean permits, and dissipates where the thermodynamic conditions withdraw. The physics is indifferent. Mawar's eye, at peak intensity, was approximately 20 miles in diameter. Within that 20-mile circle of anomalous calm, blue sky overhead, light winds, warm descending air, the contrast with the surrounding eye wall was absolute. Outside that boundary, rotating at 165 miles per hour, was a wall of cloud and wind that represented the atmosphere operating at the upper limit of what ocean temperature, atmospheric instability, and rotational dynamics could collectively produce. 20 miles in diameter, the distance from the center of London to its outermost suburbs, the distance a commercial aircraft covers in under 3 minutes at cruising speed. That is how thin the margin is between the calmest point in the storm and its most violent. 20 miles. The physics makes no concession to scale. And in the waters ahead, as the storm began its northward recurvature, the Philippine Sea still warm beneath it, the mid-latitude trough pulling it poleward with increasing acceleration. The machine was not done. Peak intensity had passed. But the storm had enough residual organization, enough vorticity, enough warm core structure to remain a dangerous system for days. The transition to extratropical status would eventually claim it. But extratropical does not mean harmless. It means the atmosphere has found a different way to use the same energy. The ocean remembers every storm, not metaphorically, in the precise, measurable sense that the thermal structure of the upper ocean retains the imprint of a tropical cyclone's passage for weeks after the system has dissipated. The cold wake left by Typhoon Mawar in the Philippine Sea in late May of 2023 persisted in satellite sea surface temperature imagery for over 3 weeks. The mixing event driven by the storm's wind stress had redistributed heat through the upper 200 feet of the water column, bringing cooler water to the surface and burying warm water at depth in a pattern that took the slow, diffusive processes of ocean heat transport more than a month to fully erase. The ocean had given the storm what it needed. The evidence of that transaction was written in the temperature field for anyone with a microwave radiometer in low Earth orbit to read. This is the nature of the climate system. Nothing is free. Every joule of energy extracted by a tropical cyclone from the ocean surface is a joule that was deposited there by solar radiation over weeks and months preceding the storm. The energy doesn't originate in the storm. The storm is the release mechanism, the valve through which the tropical ocean sheds the thermal load it has been accumulating since the previous cool season. In a very real thermodynamic sense, the typhoon season is the ocean's annual energy budget reconciliation. The global tropical cyclone record, assembled from ship observations, aircraft reconnaissance, and satellite data extending back to the mid-20th century, shows a system in measurable transition. The transition is not uniform across all metrics. Total global tropical cyclone frequency, the raw number of named storms per year, has not shown a statistically significant long-term trend in the satellite era. This is one of the most frequently misunderstood facts in public discourse about tropical cyclones and climate change, and it matters precisely because the misunderstanding cuts in both directions. Those who cite stable storm counts as evidence that nothing has changed are ignoring the variables that have shifted. Those who claim every hurricane season is unprecedented in total activity are overstating the observational evidence. What has changed? What the data shows with statistical robustness across multiple independent research groups, multiple ocean basins, and multiple observational datasets is the distribution of intensity. The proportion of tropical cyclones that reach major hurricane or typhoon intensity, Category 3 or above, has increased. The proportion that reach Category 4 or 5 specifically has increased more steeply. The average intensity at which storms reach their lifetime peak has increased. The rate of rapid intensification events, those 35 miles per hour in 24 hours threshold crossings, has increased in the Atlantic and Western Pacific. These are not projections from climate models. They are measurements from the observational record. The physical reason is straightforward and follows directly from the Carnot efficiency framework that governs tropical cyclone maximum intensity. Warmer sea surface temperatures raise the theoretical ceiling on storm intensity. A warmer ocean does not guarantee that every storm reaches that ceiling. The atmospheric environment, particularly vertical wind shear and mid-level humidity, determines how close any individual storm comes to its thermodynamic potential. But a raised ceiling means that storms which do find favorable atmospheric environments have more headroom to intensify. The record-breaking intensities documented in recent decades, Typhoon Haiyan in 2013, Hurricane Patricia in 2015, Typhoon Goni in 2020, among others, are not coincidences. They are thermodynamic inevitabilities, playing out in an ocean that has absorbed roughly 90% of the excess heat accumulated in the Earth system since the pre-industrial era. The number bears repeating, 90%. The ocean is the primary heat sink of the climate system. The atmospheric temperature increase that humans experience directly, the warmer summers, the shifted seasons, the heat waves, represents only a fraction of the total thermal energy imbalance. The ocean has been absorbing the vast majority, silently, invisibly, at depths beyond the reach of casual observation. The surface expression of this accumulation, the elevated sea surface temperatures, the deeper warm layers, the reduced upwelling cooling, is what tropical cyclones interact with. The storms are, in effect, responding to the full integrated heat accumulation of the industrial era, not merely the thin surface layer that climate discussions most often reference. This is why the changes in tropical cyclone behavior are already measurable. The storms are sampling a thermal reservoir that has been charging for over a century. The attribution of specific storm events to climate change, determining what fraction of Typhoon Mawar's intensity, or Haiyan's surge, or Patricia's record minimum pressure was directly caused by anthropogenic warming versus natural variability, is one of the most technically demanding problems in current climate science. The field of extreme event attribution, pioneered by researchers including Miles Allen at Oxford, and later advanced by groups at NOAA's Geophysical Fluid Dynamics Laboratory and the Lawrence Berkeley National Laboratory, uses large ensembles of climate model simulations to compare the probability of an event occurring in the actual observed climate versus a counterfactual climate without anthropogenic forcing. The methodology is sophisticated, the uncertainty bounds are carefully quantified, and the results for tropical cyclone intensity have been consistent. Anthropogenic warming has increased the probability of the most intense events and the magnitude of rainfall associated with tropical cyclones. The rainfall component deserves particular emphasis because it is frequently underweighted in public perception of tropical cyclone risk. A warmer atmosphere holds more water vapor. The relationship is governed by the Clausius-Clapeyron equation, which predicts approximately 7% more water vapor per degree Celsius of atmospheric warming. Tropical cyclones moving through a more moisture-laden atmosphere produce more rainfall. The attribution studies on Hurricane Harvey in 2017, which dropped over 60 inches of rain on parts of the Houston metropolitan area, estimated that anthropogenic warming increased Harvey's extreme rainfall by 15 to 40%, depending on the methodology used. Not the storm itself, not its track. The water. 15 to 40% more water falling on the same geography, on the same infrastructure, on the same population. For coastal populations living at the intersection of rising seas and intensifying storms, the compound risk profile has shifted measurably within a single human generation. Sea level rise, driven by the thermal expansion of seawater and the melting of land-based ice sheets and glaciers, increases the base elevation from which storm surge operates. A surge that would have reached 8 feet above mean sea level in 1950 now reaches 8 feet above a sea level that is, in many locations, 6 to 12 inches higher than it was in 1950. The water goes further inland. The inundation depth is greater. The drainage is slower. The compounding of these factors does not require a stronger storm to produce a more destructive outcome. It requires only the passage of time. Guam, where Mawar made its most direct impact on United States territory, sits at an average elevation that makes large portions of the island's coastal infrastructure vulnerable to even moderate surge events at current sea levels. The combination of a warming ocean producing more intense storms and rising seas, increasing the reach of those storms' surge, represents a risk trajectory that the island's infrastructure, much of it built to standards calibrated against the historical storm climatology of the mid-20th century, was not designed to accommodate. The same is true of every low-lying coastal community in the western Pacific Typhoon belt, the Marshall Islands, where the highest point on most atolls reaches only 6 feet above sea level. The northern coast of Vietnam, where dense population and shallow coastal geometry create conditions for catastrophic surge amplification. The Ayeyarwady Delta of Myanmar, where Cyclone Nargis in 2008 killed over 138,000 people in a storm surge that penetrated over 25 miles inland across flat delta terrain. These are not remote abstract vulnerabilities. They are documented, measured, physically understood risk concentrations, populations exposed to a hazard whose physical parameters are shifting in ways that the historical record no longer adequately describes. The scientists who study these systems, the atmospheric dynamicists, the physical oceanographers, the climate attribution researchers, the coastal engineers, are not issuing warnings based on speculation. They are reading measurements. The ocean heat content measurements from the Argo array, the sea surface temperature records from satellite radiometers, the tropical cyclone intensity data from reconnaissance aircraft and satellite microwave sounders, the sea level records from tide gauges and satellite altimeters, the ice sheet mass balance data from the GRACE gravity satellites. Each data set is independent. Each tells the same story from a different angle. The convergence is not the result of coordinated narrative. It is the result of a physical system in transition, expressing itself through every observational pathway simultaneously. Mawar dissipated as a recognizable tropical system in the northwestern Pacific in early June of 2023. Its remnant circulation absorbed into the mid-latitude westerlies, its warm core eroded by the cold sea surface temperatures north of 30 degrees latitude and the strong vertical shear of the jet stream. The specific atmospheric disturbance that had begun as a cluster of thunderstorms over the Philippine Sea 6 weeks earlier ceased to exist as an organized system. Its energy had been distributed. Into the ocean mixing it had driven. Into the precipitation it had deposited across thousands of miles of ocean and land. Into the altered downstream atmospheric circulation patterns it had imprinted on the hemispheric flow. The Western Pacific did not pause. Within weeks, new tropical disturbances were developing in the same waters, drawing on the same thermal reservoir, subject to the same physical laws, following the same thermodynamic imperatives. The season that produced Mawar also produced Typhoon Doksuri, which made landfall in Fujian Province, China in late July of 2023 as the most powerful typhoon to strike the region in decades, and Typhoon Kanun, which struck Japan with unusual intensity for its latitude. The 2023 Western Pacific typhoon season was not an outlier. It was a data point on a trend line that has been accumulating for decades. The atmosphere and ocean operate on timescales that dwarf human institutional memory. The warming accumulated in the ocean over the past century will continue to influence tropical cyclone behavior for decades, regardless of any future changes in atmospheric greenhouse gas concentrations, because of the thermal inertia of a water body that covers 70% of the planet's surface and reaches depths of over 3 miles. The thermal commitment, the warming already locked in by existing greenhouse gas concentrations, ensures that the storms of the coming decades will be operating in an ocean warmer than any that has existed during the entire period of human coastal settlement. The physics does not negotiate this timeline. It does not respond to quarterly reports or electoral cycles. It responds to joules. The Western Pacific is full of them.